Hello. In this video, I'll introduce the next tutorial, which also uses simple statistics for classification. Now, one of the very important uses for statistical classification is to establish a baseline, as it says in this first paragraph. Simpler is better. Let me make it a little bit bigger. Simpler is better. Even when applying more advanced machine learning classification techniques, one should always use a simple method to set a baseline for a comparison. So you should have a reference method to compare your machine learning methods to. Sometimes the simple method is better than the fancy method. So it's important to make that comparison. The simplest classification methods are based on elementary statistics. One standard statistical classification method uses the so-called Mahalanobis distance. Given an approximately normal probability distribution, the Mahalanobis distance of a data point to that distribution uses the covariance matrix of the distribution to estimate the likelihood that the data point belongs to that distribution. So this is a little bit fancy, but let me show you what it's talking about. When you have data, the data here is illustrated by the blue dots, and here you have two features, x and y. Right? So the blue dots are scattered, but they have more or less this oblong shape. Now you see several ellipses here. These are called data ellipses, and they're based on the covariance of this data. Now we don't need to go into those details, but Mahalanobis distance reflects which ellipse you're on. So any point on the blue ellipse is the same Mahalanobis distance from the center of the distribution. It actually has the same likelihood or the same probability density if you're looking at a normal distribution. But you can say that all of these points are the same distance. Now, this point, of course, is much closer to the center than this one. But if you see the way the data is spread, the density of points out here is approximately the same as the density of points here. And it's the density that determines the probability. Right? So you can imagine other ellipses being drawn, concentric ellipses that go down smaller. And as I said, the Mahalanobis distance reflects which ellipse you're on. Now, why is this useful? Well, we can look at this picture here. Suppose we have two sets of data, male and female, and we want to do a classification. So here you see two covariance ellipses, and as I said, all these points have the same Mahalanobis distance. All of these points have the same Mahalanobis distance to the male. I should have said that all these points on the green ellipse have the same Mahalanobis distance to the female center. All of these points on the blue ellipse have the same distance to the mean of the male data. So we can compare Mahalanobis distances of the different distributions. And the Mahalanobis distance that is smaller it tells us which group to assign the result to. For instance, if I take some point that's inside this blue ellipse and outside of this green ellipse, that means the Mahalanobis distance for female is bigger than the Mahalanobis distance for male, so I would classify that as male. Or you take a point here where the point is inside the green ellipse but outside the blue ellipse, I would classify that as female. Now sometimes we'll get a misclassification. For instance, here this blue point is inside the green ellipse but outside the blue ellipse. So this would be misclassified. And this green point here is inside the blue ellipse, outside the green ellipse. So that would be misclassified as male. It's a female misclassified as male. But the Mahalanobis distance gives me a measure of how close the data point is to the mean of the distribution. And the smaller Mahalanobis distance corresponds to the more likely class. Right? So we'll be using Mahalanobis distances to classify. Now, one advantage of Mahalanobis distance is that it can be used to classify data based on multiple features, whereas thresholds, using ROC curves with thresholds, can only work for a single feature. Right? In fact, the classification is not difficult to program in Python. So we will demonstrate on our classification of Rooibos into fermented and non-fermented. Recall our data is contained in the data frame DF, and the type column indicates the non-fermented as 0 and fermented as 1. Okay. So, and we'll record it in the variable y. Right? So in exercise 1, you will have to do some imports. You will also need to import the metrics from scikit-learn, and we'll import train test split, because we'll do training and testing. Now we also need to recover the variables that we created in tutorial 1. If you go back to tutorial 1, at the very end, it will show you how to use the store command to recover these variables. Now, in the remainder of this tutorial, we will construct a pipeline for training and testing a classifier. The pipeline gives a systematic procedure that takes data as input and produces an evaluation of a classifier or several classifiers as output. So the concept of pipeline is key in machine learning. It's how you evaluate classifiers, or how you evaluate predictors as well. How you evaluate any machine learning method is using a pipeline. The pipeline also enables the possibility of comparing different versions of the same classifier. This pipeline structure is very important for several reasons. First, it enables you to tune your machine learning algorithm by applying exactly the same procedure to multiple variants of the algorithm. So you can compare different variants of the same algorithm. Second, a well-constructed pipeline can be reused on other similar data. So we don't need to construct a different pipeline for different data, because machine learning data, a machine learning algorithm, after all, can't tell if the data is from Rooibos or it's from medical or from where it's from. It just treats the data as data. Okay. So this is important if you want to verify your results on another data set. Finally, the pipeline can be slightly modified to evaluate other classifiers as well, as you'll see in tutorial 4. Okay, so let's look at the feature groups that we will use for classification. Each feature group will give us a different classifier. We will look at 3 single feature groups and 1 with 2 features. Now, I said that typically you'll use Mahalanobis distance when you have more than 1 feature, but here we're just illustrating the concept, and we're doing it on single feature data. But you see here, this set of features, there are 2 features here, we'll use Mahalanobis distance on these 2 features. And hopefully this will give us a better result. At this point, we need to split the data between training and testing. The training data is used to estimate the distribution parameters of fermented and non-fermented. The testing data is used to evaluate the performance of the resulting classifiers. So training enables you to set the parameters of your algorithm. Testing tells you how well the algorithm is performing. There's no set rule for choosing the split between training and testing, although generally the training set is larger. To see which split gives the most reliable classifier, we use Jackknife, which gives error bars for each estimator's accuracy. Jackknife works by going through the training testing process multiple times, each time leaving out only 1 data sample. This produces multiple accuracy estimates, which can be combined using the Jackknife formula to obtain an estimate for the variance of the classifier's accuracy. And here's a reference for more background. So Jackknife is like cross-validation, but it gives me a specific number for the error bars, which is very important, as I've emphasized in previous videos. Okay, so first we'll list the different splits that we will evaluate. Splits are specified according to the proportion of data that's used for testing, while the rest is used for training. Okay, so here this 0.3 means that I'll use 0.3 for 30% of the data for testing, Whereas this 0.4 means I'll run the same procedure again using 40% of the data for testing. All right, so now we're going to introduce a different data structure called a dictionary. A dictionary is a Python data structure consisting of key-value pairs. So in other words, the value is identified by a key. Just like in a dictionary, you look up a word and you get a meaning. So in this case, the key will be a word, the value will be a number. Right? So let's see how this works. So we will create a nested dictionary in which keys are assigned subkeys to label specific information. Okay. In our case, the top level keys indicate the feature, second level keys give the training testing split, and subkeys indicate different performance results. So we're actually going to have different levels in our dictionary. So here's an example of a nested dictionary. The two top level keys are dict1 and dict2, or you might think this is item 1 and item 2. So under this top level key, we can specify the color and shape associated with dict1. And then here we get the values associated with those subkeys. Okay. So dict1 color is red, dict1 shape is square. We need both the top level key and the second level key to get the value. Now in our case, the values will not be words, but they'll be numbers. So that's the only difference between this example and our example. The other example is that we'll have subkeys, so we'll have more than one level of subkeys. Okay, so first we need to create an empty dictionary, which we can create using the brackets. And we are going to train and evaluate 8 classifiers, which are 4 feature sets with 2 splits per feature set. And the code will produce the following outputs for each of these 8 classifiers. So you can see that there's quite a bit of data, there's quite a bit of results involved. It needs to be well organized. We classify the total accuracy. We classify the training standard deviation, which is the error bar on the training variation. The testing standard deviation, which is the standard deviation on the testing, and the total standard deviation, which is the combination of training and testing. Okay, so to compute all these things, we'll need some accessory functions. First, we need to compute the accuracy score for a Mahalanobis distance-based classifier. And here's the code. And part of it you need to fill in. So you need to try to see what the code is doing and make the appropriate additions. So I will go through the code in this cell and try to explain what it's doing. All right? So the name of the function that's being defined is ACScore Maha. It takes 4 inputs. The training features, the training classification, YTR, the testing features, YTest, and the testing classification, which is YTest. But did I say YTest here? That ECTest and YTest. Right. So the idea is we're going to use the XTR and YTR to get the ellipse that's necessary. And then we'll apply that to the testing set. Right. So first we need the number of instances in the training set, which will be n, I'm sorry, that's not the number of instances, that's the number of features. The number of features in the training set. So that's XTR colors. That should be the same number of features in the testing set. Okay. Then we want to convert the classification, the output for the training set, to a simple array, so we flatten it. Now we want to look at the training instances corresponding to the classification 0. That's going to be one class. And we can compute the ellipse for that one class. So for example, class 0 could be the females. So we're going to take the female data and compute the ellipse for the female class. Now we'll have to do the same thing for males, so watch closely how we're doing it for females. So we're taking the data, this is for class 0. We're computing the covariance, again using the training data for class 0. Now you don't need to understand all of these details. Just follow along the variables. Okay. All right. Then we're going to shift the testing data by the mean of the training data that's in class 0. And then we're going to apply this function to that result. Now, again, you don't need to understand what's going on here. You just need to see the relationship between the label and the variables. Okay? We're using XTR0 to get the Mahalanobis distance to class 0. Okay? Now you want to do the same thing for the Mahalanobis distance for class 1. So that's what you're supposed to do here. So I would suggest what you do is you copy all of this and see what would be different if you do class 1 instead of class 0. Now notice here there's no 0 or 1 on this variable. Okay? So you want to basically replace the data from training set 0 with the data from training set 1. Okay, so as I said, probably the best approach would be to copy these lines, paste here, and make the necessary changes. Now, once you've done that, you will have two variables, Maha distance 0 and Maha distance 1. And that's going to be the same length as the number of testing instances. Now, to classify the testing instance, you're going to compare Maha distance 0 and Maha distance 1. So for those instances where Maha distance 0 is smaller, you will classify that as 0. For those instances where Maha distance is 1, you will classify that as 1. So you can use a logical statement to assign values to ypred. Now, before you set ypred, you should probably define it as a vector of all zeros, but then you'll change the value. And the value will change according to whether Mahadist 0 is greater than Mahadist 1 or not. So that's going to be your logical condition. Your logical condition will look something like Mahadist 0 greater than Mahadist 1. Okay. And that logical condition is going to select from your array. Something like this. This is a logical condition. This logical condition selected the training features that corresponded to ytr equals 0. So you want to do the same thing. You want to create ypred corresponding to this selection criteria. All right? Now, after that, then I think all of the rest is done for you. So this is the y-actual. So you'll have ypred and y-actual. You can use those two vectors to find the proportion of correct predictions. So that would be the accuracy. Remember, the accuracy is equal to the number of correct predictions divided by the total number in the data set. Okay, so that's the first function that we need. The second function is get accuracy check, which returns the accuracy score plus the standard deviations on the accuracy. So as I've been saying, it's important to get the standard deviations. Now the function we've just defined, ACScore Maha, will give us the accuracy. So we will call the function we defined above, ACScore Maha, in this function get accuracy check. Okay? So this will give us all of the results that we need to evaluate the classifier. And again, there's part that you need to fill in. So here we have get accuracy jack. And this also uses the training and the testing set. And here we get the accuracy score. Now this actually should be ACT score Maha. So I'm going to put that in. I think it's Maha like this. Let me check and see. Yes, it has an underscore. So we have ACT score Maha. So that's a correction. Now we want to compute the jackknife estimates, which will be our error bars. So we define these two variables, NXTR and NXTE. This is the number of training instances. This is the number of testing instances. So for each training instance, we will get a jackknife value. For each testing instance, we will also get a jackknife value. Now the way you get a jackknife value is you drop one of the training instances, use the remainder of the training data to estimate the one that you dropped, and then see what your accuracy score is. So let's see how that works. In this loop we have JTR, ITR, and enumerate. Now what enumerate does is it takes this list of X-train index and goes through the list one by one. Now, the values in the list will be put in this variable ITR. So the first time through the loop, ITR will be the first value in the list. Second time through the loop, ITR will be the second value in the list, and so on. Now, as ITR increases, JTR increases from 0, 1, 2, etc. So JTR gives you a running count of where you are in this list. I'm going to use JTR as an index for my output. And I'm going to use ITR to identify the item in the training set that I'm going to drop. Okay. As I mentioned, I'm going to drop one item from the training set and then use the remaining items to train and then test the resulting classifier. And what that's going to do is change the classifier slightly, and by doing this for every instance in the training set, this will give me an estimate of the variance using the jackknife formula. Right? So here I'm dropping the training instances one by one. I am using the reduced training set, X-train, to compute the estimator. And of course, if I use the reduced training set of features, I need to use the reduced training set of results as well. And I'm testing the accuracy using the same testing set. So what this does is this is going to help me find the variance due to the variation in the training. Right. Now there's also variation due to testing. The testing set has a limited size. So there's going to be error in the accuracy estimate due to the limited size of the testing set. Now that's what you're going to do here. You're going to do leave out one for testing. Now, when you do leave out one for testing, you use the entire training set. So you don't drop any training instances. You only drop a testing instance. So you'll go through the loop. Each time through the loop, you'll drop one testing instance. You'll still use the training. So you'll use the entire X-train, Y-train for your training, and you'll use the reduced X-test, Y-test for your testing. It's a little bit tricky, but if you follow what I'm saying, you'll be able to do it. All right. Now we use this information to compute the variation in your estimation for accuracy due to the limited size of the training set and the limited size of the testing set. This formula gives me the standard deviation of the accuracy estimate due to the limited size of the training set. So notice what I'm doing here. I'm using this array of accuracy estimates that I got from leave out 1 with training. I'm taking the variance, I'm multiplying by the number of training instances minus 1, and I take the square root. So that's the jackknife formula for standard deviation based on the variation in due to finite size of training. Now I want to do the same thing for testing. Okay? So what you're going to do is copy this statement and modify. Now for testing, you will use a different array and you'll use a different number of instances. Okay? So it's a similar formula, but you're doing it using the testing set. So I want to emphasize 2 sources of error, limited size of training set, limited size of testing set. You have to compute both using this formula. Okay. Now, to get the total standard deviation, since these 2 are independent sources of error, you take the square root of the, you take the square root of the square of the training standard deviation plus the square of the testing standard deviation. Now, if you understand probability theory, you can follow this because the variance of the sum of 2 independent random variables is the sum of the variances. But if you're not familiar with that theory, don't worry about it. Just implement this formula. The total standard deviation will be the square root of the square of the training standard deviation, which you got here, and the testing standard deviation, which you're going to compute below. Right? So now we've got all the information we need. We'll return the total accuracy, the training standard deviation, testing standard deviation, and total standard deviation. And that ends that function. That's the function that will give us all the data we need to run our tests. Okay, so now we're ready to run tests of different splits and features to find the best alternative. For this purpose, the following code is typical. We'll use similar codes to optimize other hyperparameters. Now, hyperparameter is a number that determines how the algorithm will operate. So the learning rate, in fact, is a hyperparameter. So the hyperparameter is a parameter that you determine before running the algorithm. To find the best hyperparameter, as with learning rate, you do trial and error. You just try different values till you get the best one. All right. So here we go with our code. Okay, so this code computes accuracies for a binary classifier based on Mahalanobis distance with different training test splits. Okay, so we will need a function that will do the training test split for us. So we import that from scikit-learn. So remember, we're trying different splits and we're comparing the results. I think the 2 splits we're using are 0.3 and 0.4. So for S in splits, we'll do those splits one by one. We will use that training test split to create a training set and a testing set. Right? Training set features, testing set features, training set label, testing set label. All right, now we're going to create our dictionary. Remember, we have a dictionary with keys and subkeys. Now, the top level key should identify which split we're using. We're looking at 2 splits, 0.3 and 0.4. Now, the splits are numbers, but we want our keys to be strings. So we convert those numbers to strings here. And here we make space in our dictionary for the entries in these keys. We already initialized our base dictionary, and now this creates space in each key for an entry. Now remember also we have several feature sets. We have 3 feature sets with single features and 1 feature set with 2 features. And we'll have separate results for each of these feature sets. So under this key 0, for each key 0, we'll have 4 feature sets. That's the next level of our dictionary. So again, we want our dictionary keys to be strings. So we take the feature sets, convert them to strings, and later on we'll put our results inside the dictionary labeled by these keys. And you'll see how that works in a few minutes. In fact, you'll see how that works right away. Here's our results that we get. Now remember, the results that it returns are the total accuracy, the training standard deviation, testing standard deviation, and total standard deviation. That was up here when we returned from our previous function. Those are the results from our accuracy test. So once we get these results, we want to store them in the dictionary. So first we have to make space under each subkey, and then we'll have one more key to identify the 4 different measurements that we make. All right? So what does this mean? This means key 0 will identify the split, key 1 will identify the feature set. Total accuracy tells me I'm measuring the total accuracy, and then this is the first result, so I do results of 0. Okay? So every data item will be identified by 3 keys. By the split, by the feature, and by the feature set, and by the type of item it is. All right? So here I've stored the accuracy. I also want to store the training standard deviation, testing standard deviation, and total standard deviation similarly. Now this is results 1, results 2, and results 3. Right? So you can copy this statement 3 times and modify accordingly to store these 3 results. Now if you want to print the output, you can uncomment this. It will give a very long and complicated printout because the dictionary structure has 3 levels, so it's a little bit complicated. But now we have the dictionary structure. It's easy to access the data that we want. For instance, if I want all the results for the split 0.4 using this feature set, this will print out 4 items, right? It will print out the 4 things that I measured for this split and this feature set. Now, if I want a specific item, I can do another key, right? So I hope this is clear how this works. It's just like a dictionary inside a dictionary. Now, sometimes you have a dictionary and you want to find out what the keys are. So this cell shows you how to do that. The top level keys are base dict, that's the name of the dictionary, dot keys, open and close parentheses. Now this is going to be a list, so if you want the first one, you'll take the first from the list. If you want to find the subkeys under the first top level key, then you would just cite the first top level key and then put dot keys. Right? Dot keys is an attribute of a dictionary or dictionary heading. Okay. Next, we store the dictionary for the next notebook. That's important. All right, so in this cell, you're just printing some output. I think the instructions are self-explanatory. So let's go down again. Now this cell here plots the information for you. You don't need to change this cell, but you do need to interpret what the cell is telling you. The cell is going to tell you estimated accuracies for the different feature sets, and it's also going to give standard deviation as error bars. And from this figure, if you interpret properly, you should be able to tell which is the better split and which feature set gives the most accurate classifier. All right. Now please read this paragraph about error bars. It's important to understand the interpretation of error bars. And this paragraph gives a particular example of how to interpret error bars. So please read these paragraphs. Now this exercise is just doing some variations of the tests that you've done so far. So I will let you read those, but if you understood correctly what happened before, these are simply modifications of what we've done already. So that's the end of this notebook, and we have one more.